Okay, let's go through this example about the Doppler effect, redshift, and the Hubble's law. Light from a distant galaxy has an emission line with wavelength 445 nanometers. The line has wavelength 410 nanometers when measured in the lab. Using h0, this is the Hubble constant, is equal to 71 kilometers per second
I can't see your screen.
per megaparsec. So it's 71 kilometers per second in the numerator divided by 1 megaparsec in the denominator. Calculate the galaxy's redshift, B its recession speed, and C its distance. So the amount of redshift, we learned the formula is given by this. Z equals delta lambda divided by lambda, and it is also equal to delta F divided by F, and it is also equal to V over C. Okay, we saw that equation when we were learning the theory. Let me show it to you. That equation is very important, and I will show it to you. Yeah, that's the equation. So Z equals delta lambda over lambda equals delta F over F equals V over C. Okay, since they have given us the wavelengths, we will use delta lambda over lambda equals Z. Then delta lambda is the change in wavelength, that is the difference in wavelength from the observed wavelength and the original wavelength. The line has wavelength 410 nanometers when measured in the lab. So this is the original wavelength 410, but what is observed is 445. You can see the wavelength here that is observed is greater than the original wavelength, meaning it is a redshift. So if the observed wavelength is longer than the original wavelength, the wavelength is greater. That means the wavelength, you can imagine, is stretched. The wave is stretched. So it's towards the less wavelength side, which means the red, ROYGBIV. The spectrum of white light, red means it has a longer wavelength. Blue, violet, indigo, they have shorter wavelengths compared to red. So if it's a blue shift, that means the wavelength should decrease. In this case, for all the stars and galaxies, generally it's a red shift because the galaxies and stars are moving away from us. So the change in wavelength, that is the difference between the observed wavelength and the original wavelength, is 445 minus 410 in nanometers, that is 35 nanometers. So Z equals delta lambda divided by lambda. Delta lambda is 35, that is the change in wavelength in nanometers, and this lambda here is the original wavelength, that is 410 nanometers. So 410 nanometers is the wavelength of the waves that this galaxy emits, but what we observe is 445 because the galaxy is moving away from us. Now how do we know that it is moving away? Because the observed wavelength is greater than the original wavelength. So if it's moving away, you can imagine the waves are stretched. So that's why we observe a longer wavelength. Okay, then Z is the amount of redshift. So that is the answer to the part A, 0.0854. Now you can see the units here and the units here, they cancel out. So there will be no unit. By the way, this should be simple nanometers, not millimeters. Part B, it's recession speed. The recession means it's moving away. The speed with which this galaxy is moving away from us is what we are supposed to find in part B. So we have also we have Z equals V over C. Now remember, Z equals delta lambda over lambda equals delta F over F. Now also we have Z equals V over C. So we are supposed to find V here. That is the recession speed. That is the speed with which the star, or in this case the galaxy, is moving away from us. Now why we say us? Because this is observed, this light from the galaxy is observed when we are on the earth. So that's why we say moving away from us, the speed with which it is moving away from us. Okay, so we have C times Z. Now C is the speed of light, which is 3 into 10 to the power of 8 meters per second, the speed of light in vacuum, and Z is the amount of redshift. So what we used was Z equals V over C. We made V the subject of the equation, and then we found what V is. Okay, so actually they should have written this first and written this second because it's in this order. So C is the speed of light, Z is the amount of redshift, which we found in the previous part. That is what you see here. Then we get 2.56 into 10 to the power 7 meters per second, which is in kilometers per second. You divide by 1000 and you get 7 minus 3, which is 4. Yeah, divide this by 10 to the power 3, divide by 1000 and you get 10 to the power 7 minus 10 to the power 10 to the power 7 divided by 10 to the power 3, which is when you divide, you subtract the powers, which is 7 minus 3, 4. So you get it in kilometers per second. And then the last part, it's distance. So for this we can use the Hubble's law equation, which is V equals h naught d. V is the recession speed, d is the distance, h naught is the Hubble constant. So V we found in the previous part, which is this in SI units, and h naught is the Hubble constant, and that is given 71 kilometers per second per mega per second. Now in the theory part we learned about this unit also. Okay, let me quickly go through that. There was an example where we converted the unit of Hubble constant to its SI units. See, this was that calculation. Now here you can see this is the Hubble constant in these units that they normally give, and this actually here you can see they first converted it to meters per second, this part, and then this per second to the power minus 1. So that means this whole thing is divided by megaparsec. So first thing is they converted this to from kilometers to meters, and then you can see what 1 parsec is. It is this much. So this part here is equal to that, and then 1 mega means 10 to the power 6. So you multiply this by 10 to the power 6, you get 10 to the power 22 here into 3.09. Then remember h naught, this here is in is meters per second, 70,900. Then that whole thing is divided by 1 megaparsec. Okay, why? Because of this power minus 1. That means it's that power minus 1 applies to this whole thing from here all the way to here. Okay, then we can write that at the bottom 1 megaparsec is this much, and then you get this. So you see the units will cancel out and you will get in per second. All right, so that anyway, what happens is we are not converting it to SI unit, so we give the answer, distance answer in the unit megaparsec. Parsec is a unit of distance. Okay, over here also we had the graph of velocity of recession versus distance. The gradient of this graph was the Hubble constant. Okay, so that's the end of that example, which covered the Hubble's law. Okay, this equation over here, Hubble's law, and it also covered the redshift. Yeah, this one, the amount of redshift is given by this equation, so we use this as well as this one. And also we learned about Doppler effect. So it's, if it's moving away, the observed wavelength is greater than the actual wavelength, which you see here. This wavelength is the observed wavelength, it's greater than the original wavelength. Okay, so that's the end of that question.